Okay, good. So I'm just sharing the screen, yeah? Do you see my screen now?
Yes.
Okay, good.
Yes.
Okay, so thank you very much. And thanks for this opportunity to give a talk. I will try to make it concise in 30 minutes, even though the work seems to be quite bulky, in which we computed non-Gaussianity in analytic infinite derivative gravity. And this is practically the main topic of my talk. It is consideration of R-squared-like inflation, so Starobinsky-like inflation. The paper was written recently in collaboration with Alexey Starobinsky himself, as well as Sravan Kumar and Anupam Mazumdar. And in this paper, we have considered the analytic infinite derivative gravity and the consequences to inflation, in particular, interesting consequences to tensor tilt and non-Gaussianity. But before I will start with all of that, let me try to explain what the theory is. So as you see here, there is some short list of problems which led basically us to this modification. And the grand problem is that Einstein gravity is not UV complete. So in simple words, it must be modified somehow. And we know two developments, one by Kelly in 1977 and 78, when he showed that R-squared gravity can be renormalizable, but with the price of a ghost in spin 2 sector. Another development roughly the same time by Alexey Starobinsky was construction of brilliant model of inflation based on R-squared gravity, which perfectly works. But as just said, it is not a UV complete yet model. And aiming to UV complete at higher energy scales, we need some modification of gravity anyway. And here there is some short list of names and keywords on the way which led us to this development. And maybe one of the main keywords is here, which is string field theory, which gave us motivation to consider high derivatives and especially infinitely many derivatives in the action, as well as names of people who contributed to the topic, as well as many others whom I just have no space to list here. But even if we don't go to string field theory, we always can find out that there is a little bit simpler approach to the problem. And here it is. Let us try to consider this action, which is not restricted in any way. It's summation about everything with respect to products of everything, where there are some quantities depending on curvature and operators depending on covariant derivatives. So practically speaking, it's everything what you can imagine to write, as long as you base on Riemannian curvature. So it's quite a huge zoo of possible theories. It's still not complete because it does not include something which has like 1 over box operators, because I aim to target high energies, so ultraviolet. Okay. We somehow started to name it some general analytic gravity because it contains everything which depends analytically here either on Riemann tensor or on covariant derivatives. This looks like really untractable start, but if you try to ask a question, what would be an action which is responsible for fluctuations around maximally symmetric spacetimes, which are in principle Minkowski and de Sitter and anti-de Sitter, then you will find out this action, which is written here in 2 lines. The first line is very simple. It's Einstein term and cosmological constant term. And the second line is essentially the modification which we were seeking. And this was found in this paper in collaboration with Tirta Biswas and Anupam Mazumdar. Sorry. And here, sorry, I just touched the touchpad. And here you see we have three terms. All of them are kind of similar. Each of them is quadratic in curvature. Here is in scalar curvature. Here is in tensor, in second rank tensor L menu, and here is in fourth rank tensor, which is we have chosen to be Weil tensor for simplicity. And all of these terms are somehow sandwiched with some operator functions of box, where box is a D'Alembertian operator. Because we have started with something analytic independence with respect to derivatives, it means that a corresponding f of box is some analytic function of its argument, so practically speaking of D'Alembertian, and analyticity at 0 guarantees that we have smooth infrared limit. This was one of the requirements. So smooth infrared limit is guaranteed here. Ultraviolet is modified. And even though it still looks kind of cumbersome, we can do something. And this something is not too few. For example, we can start with extracting propagators of spin 2 and spin 0 modes. And this is how it looks like. Here is a spin 2 mode, H mu transverse and traceless, which is denoted by this sign perpendicular. And what we notice here that we have done here expansion around maximally symmetric spacetime, so practically speaking around the Sitter space. It is a canonical factor in the kinetic term, which is box minus R over 6. And then there is an operator P of box, which is written here, which is comprised out of three terms. The first one is unit, it's just from Einstein gravity. The second one in green color, I hope you see it a little bit green, it is the term which would come in, would you have just a local R squared modification. And the third one is a term which comes in as long as you have the function Fw. Fw, as it is here, is a function which is in between of Weil tensors. So as long as you have this function Fw, you gain this term. Okay. Now, what was done by Koshelev in 1977? He considered R squared gravity, and he was forced to add Weil squared term in order to gain renormalizability. As you see here, just a local Weil squared term corresponds to function Fw, which is here equal 1, which essentially means that this red multiplier is equal 1. And this essentially means the whole operator P is equal to this expression, which is nothing but box plus a constant, which in a sense is a second pole in the propagator, which we know for already 150 years, thanks to development by Ostrosky, is a ghost. There is no other way, but one of these excitations would be normal, another would be ghost. Scalar sector roughly features the same structure. All the same strategy applies to analyzing the term. It has the scalar mode phi. It has this canonical 3 box plus R kinetic operator, and it has the operator S, which would be 1 in Einstein gravity, which would have this green term given we have local R squared gravity, and which would gain this red term as long as you consider some non-trivial FR theory. No, sorry, FR operator. Some non-trivial non-local modification in R squared sector. Here we know that in Einstein theory, scalar mode is a ghost. It's a gauge degree of freedom. It doesn't affect anything. But this exactly means that would we gain some another degree of freedom here, this would be not a ghost. And this is exactly our scalar mode in local F of R gravity. It would be just a simple consideration, would FR of box be equal 1? But here it is much more complicated. A natural question here is that whether we introduce high derivatives, most likely we introduce new degrees of freedom. And now let me try to explain you why we can avoid it. But before I will explain this, I will repeat again that we already know for almost 150, already 170 years actually, that Ostrosky has found that more than 2 derivatives will lead to ghosts, even though he didn't say what will happen if we have infinite number of derivatives, as well as we know that there are theories like Horndeski theory, for example, which avoid ghosts by means of some heavy fine-tuning. So it's not generically a problem to avoid a ghost, even with a finite number of derivatives. But coming from the subject which I came from originally, which is string theory, we have some idea why to include infinite number of derivatives, and here how it goes. You see, in gravity action, which I have presented, technically speaking, box minus m squared was replaced by some function g of box. This is the idea which can be exploited there. This is phi box minus m squared. Phi is a good field Lagrangian. Good means that it is not a ghost. It has proper sign plus, as long as we have minus plus 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 signature. And this is an example of not so good Lagrangian because it has two poles, one at m squared, one at mu squared. One of these two will be definitely a ghost. And here there is another proposal, that this function g of box can be box minus m squared, as it was, multiplied by some exponent of entire function. It's essential here to have exponential of entire function because this is the only mathematical construction, like this exponent of sigma of box. This is unique mathematical construction which doesn't produce you pole on the whole complex plane, as long as it is inverted, because exponent of entire function doesn't have zeros. And this is, at the bottom, is generically the Lagrangian, which would simultaneously have infinite number of derivatives and does not introduce any new degree of freedom in our consideration. This exactly can be used to somehow express back here this function f of fr, or here fw. So the idea is simply to equate this line, this p of box, for example, to something which looks like this bottom line, like box minus m squared exponent of sigma. Okay. In case, however, of p of box, which is graviton propagator, we would need to have just box, not box minus m squared, because we want to preserve graviton to be massless. This is the idea. And this is practically the only way here to avoid a ghost, as long as you include Weil squared piece. And as long as you want to preserve Riemannian geometry, as long as you want to preserve diffeomorphism invariance, etc., etc. So staying on these basic principles, this is so far foreseen as the only way to preserve theory to be healthy. And this is exactly the same picture coming from totally different point of view, which is string field theory point of view. And of course, I'm not crazy to go now inside of string field theory business, but what I want to mention, this is exactly what string field theory usually gives as an outcome for some computations. That considering scattering of string modes, canonical kinetic term for some field phi would be accompanied as well by some heavily non-local and momentum-dependent interaction vertex, like here, like exponent of some function rho, acting on field phi, and these to some power. Here I presented some example, which is not exactly everything what you can get, but this is how, for example, scalar modes scatter in string field theory. Obviously, field redefinition exponent of rho acting on phi equated to some new field phi would give us again non-local kinetic term like it is written here with some entire function accompanying now multiplying actually canonical box minus m squared, and now with a local vertex phi to the fourth. So you see, there is some deep theoretical argument which tells us that in principle structures like this can be found. Now, can we do something in this theory of gravity? So the question now which we raise is the following. Coming back to this action, which looks really cumbersome and has a lot of things apart from Einstein term, because it has a lot of different structures, and honestly speaking, equations of motion are really horrible if you write them down, even though you can. The answer is yes, we can do. And here is an example of what we can do. We can find some family of solutions by employing the following relation imposed on scalar curvature, which looks pretty simple. It says that box R, so the Lambertian action on scalar curvature, is just again proportional to scalar curvature with maybe some additional constant. In this case, especially given you consider conformally flat solutions, you can find that any solution which satisfies this relation box R equal R1R would give you some algebraic conditions like this, f prime at R1 equals 0. This one means derivative with respect to argument, as well as this connection between function f evaluated at point R1, its zero Taylor coefficient, and parameters R2 and R1 in this ansatz, and mass Planck, which originates from the Einstein term. So given these conditions satisfied, you immediately have this ansatz to solve the whole equations of motion. Now,
Excuse me, just a reminder that you have 50 minutes until the end.
Yeah, sure.
Yeah.
I'm already in the middle somehow. So you see, we have box R equal R1R solving highly non-trivial, very lengthy equations of motion from action of gravity with infinite many derivatives. And moreover, we remember that box R proportional R1R plus maybe R2 is nothing but a trace equation of just a local R squared gravity. So the claim at this moment is the following. Our new action includes all possible solutions of R squared gravity, as well as maybe impossible solution. When I say impossible, I mean solution here. It may happen the following strange story, that solutions which would be not physical in local R squared gravity because they generate some ghost, for example, stage of evolution, may become totally eligible here because parameters got changed. As such, we can make use of this fact because we know that original Starobinsky model is based on R squared gravity. It was a model without a cosmological constant. From this last relation between lambda capital and R2, we understand that absence of lambda results in R2 equals 0. Ansatz gets even more simple, like box R equal R1R. And as long as we substitute solution by Alexey Starobinsky here, we should get again the same solution satisfy, but now new equations of motion, as long as we can guarantee that f prime, so derivative of form factor f evaluated at R1 is equal 0, and some relation between Planck mass and value of R1 multiplied by f of at R1. So you see, technically speaking, we doesn't have to do anything. We just have to satisfy algebraic relations. Now the question is whether we can find appropriate form factor. And here there is an example how it looks like. This is our form factor. This is exponent of gamma, this very much new and very much important ingredient, which is exponent of entire function. This is a multiplier 1 minus box over m squared, which guarantees the presence of one massive degree of freedom, which is a scalaron of Starobinsky model. And the box in the denominator is not harmful. One can easily check that this box is being cancelled by Taylor expanding what is inside of brackets. So the function f of box is analytic. And as such, we have satisfied every condition we demanded from the very beginning. It should be analytic, it should not provide extra poles, and it should organize, in our case, one massive degree of freedom, which is scalar. Then we can find by some algebra, we can find that R1 from our ansatz is equal mass of the scalaron squared, as it is exactly was in Starobinsky scenario, as well as some restrictions on function. Oh, sorry, it should be written gamma here. I'm sorry for this misprint. It should not h0, it should be gamma here. This gamma, this entire function, the exponent, which guarantees that these conditions are satisfied here. Having this done, we can go further and we can do some computations. Well, not all these computations were done in the paper which was announced at the beginning of the talk. Of course, some of them were done a few years ago, but the point is to present outcome, which is here, which is power spectra. This is power spectrum for tensor modes, delta H squared, and this is delta R squared power spectrum for scalar modes. Generically, it's not a surprise, but since we speak about two-point function, scalar power spectrum is not modified, so it is the same. As such, we expect the scalar tilt to be roughly the same, NS. Things differ, however, for tensor power spectrum. Tensor power spectrum got modified, and exactly this exponential factor is a new factor which we gain upon computation. This omega comes from the fact that P of box should be equated to exponent of omega. Let me scroll a little bit up and remind you that P of box is nothing but this new operator. I must equate it to be equal exponent of 2 omega, where omega is entire function, in order to guarantee that this operator produces no new poles. So graviton remains graviton. However, it manifests here upon canonical normalization of fields, and this factor arises here, and this is how it looks like. So essentially, we get some modification here, which would be some number which can be fixed upon further consideration of the theory. The same happens to, obviously, tensor-to-scalar ratio, because it's just division of delta H squared to delta R squared. And we see that tensor-to-scalar ratio gets modified from local case, because in a local case, it would be 12 over n squared, which we pretty much know it should be. Here, however, it gets some multiplier. On the other hand, we know that the local model answer is very well observed, and as such, we cannot go much far away from it. So this somehow fixes, but not yet completely, this factor, because we don't know how to fix it yet, as long as it is not just a factor, it's just a value of function at one given point. Still, we are happy to see that we, of course, certainly can do it, because we have a lot of freedom to select our entire function omega here. Tensor tilt becomes even more curious in this case, because compared to a local theory, where we would get just minus 3 over 2 n squared, and n is a number of e-folds during inflation, which is usually taken to be 55 or 60. Here we get another term which is exactly proportional to multiplier gamma 1. Gamma 1 is the first derivative of function gamma, and gamma is entire function which we need to introduce in order to arrange this operator. Here it is, this S of box, to produce not too many new poles. We need only one pole. We need scalaron. So in order to suppress all the rest possible poles, this is the function gamma, and this first derivative centers here in computation of tilt. Also, it can be understood in the following way. We somehow gained now, if we try to imagine transition to Einstein frame, it's obvious that our scalar field would have momentum-dependent vertices. interaction is not anymore a potential, strictly speaking, and as such, what we gain momentum dependence in potential, in interaction, better to say, and as such, we have some impact of this, and impact of this is presence of extra terms like here. And as long as we don't know what is gamma 1, and honestly speaking, there is no clear way how to fix it and pin down what is functions gamma and omega are, it seems that for the time being, we can organize in this approach either red or blue tilt for tensor modes, which was essentially not possible in a local model with a single scalar degree of freedom. And actually this, almost the last, let's say, theoretical slide is a computation which was a sense of our last paper announced at the beginning of the talk about non-Gaussianities. We made it possible to compute 3-point correlation function in this model. And here is the answer. Here is a particular answer for FNL in a squeezed limit. The first line, the first term, is exactly the local result which one would obtain in a local model. All the rest, these two terms on the second line, which essentially depend on gamma s at point r over 4, as well as r itself, as well as gamma prime at r over 4, where r is a curvature during the time of inflation. This is our modification, which certainly can be somehow tuned as long as we have enough observational data, tuned in a sense that we can try to say something about function gamma as here. We have enough freedom to make non-Gaussianity large, as well as we have enough freedom to make sign of FNL to be either positive or negative. As such, we kind of ready to new observations which are on the way, hopefully in coming years from new experiments. So what has been done? So how can I conclude all of this? What was presented is some attempt to target problem of gravity quantization with the aim of, with the help of analytic infinite derivative theories. Analytic infinite derivatives seems to be crucial ingredient here, and we have some motivation to this from string field theory, which can be said to be more fundamental stuff. The theory itself features a lot of nice properties. One of them is outlined here. It's embedding of Starobinsky inflation, which was done in this and several previous papers in collaboration with Alexey Starobinsky himself. But on the other hand, there are some other nice features like, for example, regularity of Newtonian potential and presence of non-singular and ghost-free bound solutions. In particular to inflation, we see that we have modification to tensor-to-scalar ratio R, as well as tensor tilt, and to parameters of non-Gaussianity. Modification, I mean, compared to local model of Starobinsky, as well as many other models which feature so-called consistency relation discussed by Maldacena some time ago. And ability to embed inflation also tells us that there's following hierarchy between mass of scalaron, Hubble parameter during inflation, scale of non-locality, MS, which should be present in this model, as well as Planck mass. This hierarchy should be obeyed in order to first have the model, make this model to work, and second, not to spoil what we already know. And yes, as I have mentioned already, there is connection to strings, which may be not the best, but nice property, given that stringy people do a lot of theoretical work around. And still there are, of course, open questions like, for example, quantum field theory business in such theories, given that we have to have infinite derivative form factors in Lagrangians. With respect to gravity, it's still curious to see whether we can demonstrate absence of singular solutions, because for the time being, we just can prove that non-singular solutions cannot be solutions of equations of motion here. Sorry. Why is it so exact? As well as we need to deeper study inflation and bouncing scenarios, and especially study of inflation is on the way currently. And there is some ambitious goal to see whether we can really connect in a rigorous way strings and what has been presented here with respect to gravity. So with this, I thank you very much, all of you, for listening. Thank you.
Thank you very much for your talk. So are there any questions?
I have a comment at page 8, now, which is the page with Ostrosky.
Yeah, is it here? I think here, yeah.
Okay, so just now, as a comment, now you say that it forbids higher derivatives, i.e. But no, I would say that the correct statement is different. Now, what Ostrosky shows is that the classical Hamiltonian can be negative. This is what Ostrosky has really shown. No? But physics is not classical, and negative energy maybe it's not a problem.
Yeah, generically negative energy maybe is not a problem, but at least at free level, definitely this, yeah, of course I understand that Ostrosky himself didn't show that much about field theory at least, but he has shown practically that sign of kinetic terms would be different for effective particles, because he considered one just time dependence, okay? Yeah, but for fields, we know that this results in presence of ghosts. It maybe is not a problem in an effective theory, but the global goal here is to try to treat this theory finally as a quantum theory. This may raise concerns. This is why we try to avoid it.
So you know nothing about now the quantum theory. No? For example, fermions have negative classical energy, but they have positive quantum energy. And second, you don't even know if negative energy is bad. Now, for example, vacuum decay is negative energy, but you can be metastable.
Alessandro, can I ask a question to you and then a question to the speaker? But what is the kind of most complicated theory with unbounded Hamiltonian which behaves sufficiently well? Leaving aside probably fermions, because fermions solve this by by Dirac way, in a non-fermionic way. What's the most complicated example where it is known the theory is good?
Next paper.
Sorry?
Wait 1 month, I will write.
Okay, great. Waiting.
So for the time being, as long as we can avoid ghosts, we try to avoid them, because I think if we can avoid ghosts, it would be simpler than try to explain how to live with them, at least in this setup.
Mm-hmm.
Okay, can I ask a question?
Sure.
My question is, as I understood, you tune your functions in such a way that around inflationary background, you don't have ghosts. But what about flat space background at low energies, say? Do you have ghosts, or how you tune this?
At low energies, we technically should not have ghosts, just because we will not consider these functions at all, because a scale of high derivative modification would just kill these terms, and we will live with Einstein gravity, which is without ghosts.
Well, this is true, but you have different backgrounds. You have inflationary background around which you compute everything in the last paper. And also you have a background with a zero scalar field now.
But for the time being, I didn't say that I'm obliged to tune these functions once and forever. This tune is the function itself, may be function of the background, as it is actually, because here it depends on the inflationary curvature.
But this is the way of definition of the theory. Then you have to prove that this is good, I mean, from the point of view of quantum field theory and so on.
Yes, we have to prove. We did something on this way with Leonardo Modesto, for example, and Laszlo Frashwell and Stravan, but we can do everything at once. We can do a lot of things, especially around flat space. This we can do a lot, but as long as we move further, we understand that this function has chance to depend on the background itself. For example, on the curvature of the de Sitter. But we are not obliged to have quantum theory everywhere. We have to quantize at some vacuum and then see how it evolves to other states.
Alexey, probably a related question. So just probably it's obvious, but still. So you had some complicated theory and you had formulated what you call the inflationary background. The naive question. So does it obvious that you have a solution that matches to post-inflationary expansion, that you have a solution that is realistic? So inflation plus something arriving to slowly expanding the universe. Do you have such a solution?
We have an idea.
That it has
yes, we have an idea in progress how to make it happen. It's not yet written in full, let's say, but yes, we have an idea how to do it, especially given that at a very late stage, we just will drop everything related to high derivative modifications because we don't observe them.
Yeah, that's a bit connected to what Tanya is asking.
Yes, sure. No, you see, the point here is to understand that we don't expect quantum gravity at low energies.
Yeah, for sure.
Low energy here, okay? But we want this model to be able to have UV completion somewhere. As long as we go down in energies, we kind of more and more treat this setup as an effective theory. This is the take on the problem for the time being. Or in other words, I'm not obliged to quantize theory everywhere. I oblige it in a vacuum.
No, you want to quantize it on top of the background that you have, right?
Yes, but
so if you have a good background and on top of that the theory is okay, you don't care if it's okay or not on all possible backgrounds. Okay, that I can buy.
Yes.
It's a bit a pity because it makes it hard a bit to think about the theory, which is okay. Normally, you think about a theory in terms of function, say functional integral, and then it's automatically quantized every way in some sense. But, okay, I may believe that there are vacuums that are not really vacuums, so they're classical vacuum solutions, but they're not really quantum that I can believe. One more question so returning to the old story with the infinite derivative actions. So you need entire functions. So you need functions that don't have additional poles anywhere except for infinite momentum.
Yes.
Are there any requirements on the behavior of your functions at infinite momentum?
There is not any requirement because, as a matter of fact, it will be essential singularity, and you can.
That is an essential singularity, but it's irrelevant what it is.
No, it is not irrelevant, and there are ideas first outlined by Terry Tumbulis that you are better to have some entire function which arranges you still polynomial growth at infinity. Exponent of it would be polynomially growing along real axis. This will make your life way simpler in defining whatever related to quantum computation.
Yeah, because the next question is, say, how in this series, but that's probably going a bit beyond the current topic, but still, how in this series they some what normally you think of expect from unitary theories, like say optical theorems and things like this, how they're modified in your cases.
They are modified. They can be found in this or other setup how they work, and some of this was done already. For example, by Leonardo Modeste and his group.
Mm-hmm.
Something will be done by me and Anna, I hope, in some work in progress.
Mm-hmm.
And this can be defined. The guiding line for the time being is a couple of nice papers by Ashok Sen and Pius, if I remember correctly, the second author.
Mm-hmm.
They have provided some way how to, essentially you are going to modify Feynman prescription a little bit in order to account essential singularity at infinity.
Mm-hmm. Mm-hmm.
Yeah, I mean, nothing is priceless. You have to modify something, but this modification can be done in a rather consistent way, I would say.
So you retain unitarity, but you on the price of losing locality, something like this, right?
Yeah, but losing locality was
yeah. Oh, you don't have
idea.
locality from the beginning.
Yeah, we don't.
And yeah, speaking about causality is a bit in that the moment you lose locality, you don't speak about causality at the same time. Okay.
And you see, in a sense, there is scale, this MS. So somehow below this scale of high derivative modification, you preserve everything what you expect to have, but at energy is higher, you kind of in the blue because you don't know what it is exactly, and we don't presume that. So in some sense, it's related to papers about microcausality and losing. In some sense, it's not the direct.
Is there proof that you have macro causality? Or can it be at least verified and with some finite effort?
I believe it can be verified with finite effort. No, I don't see any problem with it.
No, just interesting, because it's interesting it's interesting to be sure that macroscopically you look like a normal theory.
Yeah.
And at what moment I should notice experimentally that your theory looks peculiar?
Sure. Yes, this can be done. Yes.
That's the next question. So probably, probably I should stop because we are moving towards extra derivative discussion.
Right. Any more questions? If not, let's thank the speaker again, both speakers actually, and be back next time. Thank you for listening.